One of the important things to consider throughout the rest of the class is the idea of rewriting a function first before trying to apply some of the calculus rules to it. In the next example, these four situations all look very similar, but it's really important to kind of pay attention to the use of parentheses and rewriting things in an orderly and efficient way. In example 6, we want to find the derivative of each of the following functions. Again, we want to take the first step of rewriting this. We have the fraction 5 halves, and we want to make it look like x to a power. I can remove the x from the denominator by doing the reciprocal, which allows us to rewrite this as 5 halves x to the negative 3. Now that we're set up, it looks like a constant times a power of x. We can use the constant multiple rule, which says that the derivative is going to be equal to the constant times the derivative of x to the negative 3 halves. Power rule says you bring the power down, reduce the power by 1. So it's going to be equal to negative 15 halves x to the negative 4th power. And then let's rewrite it, because we don't want to leave our answer with a negative exponent. We're going to have negative 15 divided by 2x to the positive 4th. That will be our derivative y prime for this one. In part B, we have y equals 5 divided by 2x cubed, where this time it's the entire expression that's being cubed in the denominator. Our rules from algebra, we know that that's going to be the product to the 3rd power. So that's going to give us 2 cubed, which is 8, and then x cubed is simply x cubed. We can again rewrite it. We want it to look like a constant times x to some power. So we have 5/8 x to the negative 3rd. And now we can go ahead and take our derivative. Y prime is going to be equal to, we have 5/8, bring the negative 3 down, reduce the power by 1. So we get 5/8 times negative 3x to the 4th power, which is going to end up giving us negative 15 divided by 8x to the 4th. So that's our derivative y prime for this function. Let's take a look at part C. Here we have y equals 7 divided by 3x to the negative 2nd power. We can again rewrite this. Let's bring the x out of the denominator. That's forming the reciprocal, so that's going to change the sign of the exponent. So this function y is equivalent to 7/3 x squared. We can now go ahead and apply our derivative rules. Y prime is going to be equal to 7/3 times the derivative of x squared is 2x. So we get 14/3 x. Let's take a look at part D. In part D, the entire denominator is being raised to the negative 2nd power. So we can remove that, get that entire expression out of the denominator, move it into the numerator, and now that will change the exponent to be a positive 2. If we take 3x and square that, that's going to produce 9x squared. And then we can multiply the 7 and the 9 to get 63x squared. Okay. Very important to realize and to keep in mind that we haven't done any calculus yet. That was simply all algebra in order to write it in a form that makes it easy for us to apply our calculus rules. We have our constant multiple rule, which says we can keep the 63 as it is. The derivative of x squared is 2x. And then 63 times 2 is going to give us 126x. So for this function, the derivative, y prime, is equal to 126x. Theorem 3.5 tells us how to take the derivative of the sum and difference of two functions. Simply put, the derivative of a sum or difference is going to be the sum and difference of the derivatives. So if we take f plus g of x and we want to differentiate that sum, it's simply going to be the derivative of f plus the derivative of g. And similarly, the derivative of the function f minus g is simply going to be the derivative of f minus the derivative of g. And with this theorem and our previous rules, we'll now be able to differentiate any polynomial. Let's take a look at example 7. Let's find the derivative of f of x equals x cubed minus 4x minus 5. Here we have a sum and just a difference of a bunch of terms. That previous theorem says that we can go ahead and just differentiate each term individually. The derivative of x cubed is 3x squared. The derivative of negative 4x is negative 4. And the derivative of any constant is, of course, 0. Typically, I wouldn't write this, but just to kind of emphasize and review that fact so you're reminded of it. But here's our derivative. F prime of x is equal to 3x squared minus 4. Let's take a look at part G. This is, again, another one of these polynomials. And we might want to take the minor step of rewriting. We don't want to think of fractions quite yet. I can think of x to the fourth divided by 2 as being the same thing as negative 1/2 x to the fourth plus 3x cubed minus 2x. And now we're going to find g prime of x by differentiating each term individually. We have the negative 1/2. The derivative of x to the fourth is 4x cubed plus 3 times the derivative of x cubed is 3x squared. And the derivative of negative 2x is simply negative 2. So g prime of x is going to be equal to, a little bit of simplification here, negative 1/2 times 4 is negative 2, x cubed plus 9x squared minus 2. Let's take a look at one more in this subset. We want to take a look at the function y. Again, we're not quite ready to do the derivative of a fraction where we have variable functions in the top and bottom, but we can split this apart to create a bunch of individual terms because we simply have one term in the denominator of this fraction. So again, we're taking that very important step of rewriting it first. So this function, we're calling it y. Y equals, this is going to be 3x minus 1, and 1 over x we can rewrite as x to the negative 1 power. We are now going to take our derivative. The derivative of 3x is going to be just 3. The derivative of the constant 1 would be 0. And then the derivative of x to the negative first is going to be a negative x to the negative second. So we have 3 minus 1 over x squared. That would be our derivative for this function. The next theorem we're going to look at is going to be the derivatives of some of our trigonometric functions. The derivative of the sine of x is equal to the cosine of x. And the derivative of the cosine of x is going to be equal to negative sine x. So two derivatives are kind of closely related. Derivative of sine is cosine, whereas the derivative of cosine is going to end up being negative sine. In example 8, let's find some derivatives. We said that the derivative of sine is cosine. Therefore, for this function, y prime is going to simply be 2 cosine x. In part B, we want to take that first step of rewriting it. Sine of x divided by 2 is equivalent to 1/2 sine x. If we take the derivative, it's going to be 1/2 times the derivative of sine of x, which is cosine of x. For part C, the derivative of x is 1. And remember, the derivative of cosine of x, that's going to be equal to negative sine of x. We now come to part D. F prime of x is going to be equal to, the derivative of cosine is negative sine. Now pi over 3, again, that's just a constant. So we're going to keep the constant. We still have the negative pi over 3 times the derivative of sine, which is simply cosine of x. So f prime of x is equal to negative sine x minus pi over 3 cosine x. We now come to what's one of many calc students' favorite derivative rule. This is theorem 3.7, which is the derivative of the natural exponential function, and might be either extremely boring or extremely exciting depending upon how you look at it. But the derivative of e to the x is simply going to be equal to e to the x. So e of x is a function that turns out to be its own derivative. For example, if we look at part A, the derivative of 3 e to the x is simply going to be 3 e to the x. If we look at part B, here f prime, we have a sum of terms. It's just going to be the sum of the derivatives. The derivative of x squared is 2x, and the derivative of e to the x is itself going to be e to the x. Let's take a look at part C. F prime of x is going to be equal to the derivative of sine of x is cosine of x minus the derivative of e to the x is e to the x. So a couple brand new derivative rules this section for our trig functions and also for e to the x.